My name is Michael Katz. I'm a third-year PhD student in the Department of Physics and Astronomy. Today I'm going to tell you how and why physicists and astronomers are beginning to listen to the universe so that we can find colliding black holes. Why are black holes black? Black holes are objects that are so dense that the gravity on their surface is so strong that light, which is the fastest thing in the universe, cannot escape it. Now, if no light can escape its surface, it must appear to us to be black. Now, this has major ramifications on our ability to observe these objects with light telescopes. We can use certain methods to make inferences about their properties, but that's about it. We cannot directly measure them. This is where gravitational waves come into the picture. Gravitational waves are the sounds of the universe. They are what we are now listening to. I'd like to try to explain them with a quick example. Light, when it leaves the sun, takes about 8 minutes to get to the Earth. And as I already said, light is the fastest thing in the universe, so nothing can travel faster than that, and that includes gravity. So we're all going to do a thought experiment together. Let's imagine that the Earth is orbiting the sun in its regular orbit, and the sun instantaneously disappears. It goes away. Now the question is, would the Earth know that the sun is gone and that there's no longer the sun's gravity acting on it? Would it know immediately, or would it take 8 minutes? The answer is that it would take 8 minutes. What would happen is the Earth would be in its orbit, the sun would go away, and the information that the sun is gone would begin to propagate at the speed of light towards the Earth, arriving at the Earth 8 minutes later, just like light traveling from the sun to the Earth. Now this process, what it is effectively, is gravitational information that the sun is gone, traveling from the sun to the Earth as a gravitational wave. It is the exact same thing as light information carried by a light wave. So here I'm going to show you a video that has two black holes orbiting each other and then eventually colliding to form a single black hole. And what you're going to see is gravitational waves leaving this pair and going out into the universe. Now what you can see below the video is the waveform that we eventually measure. So if you look closely, you can see these waves going out in every direction, out towards the outer universe, and they will travel hundreds of millions to billions of years across the universe, and then eventually go through our detectors where we will measure them, which is quite remarkable. Now here I'm showing a couple different gravitational wave detectors. Some of them are already in use, some of them are future. I'll get to those in a second. First, I'd like to explain a little bit of how we listen to the universe and why these detectors are different. Light telescopes are much like our eyes. You have to point them to see things. If you want to see something with your eye, you have to point your eyes at an object and receive the photons from that object so that you realize it's there. This is why you cannot see anything that's behind you, because there's no way to get photons from behind you into your pupils so that you can see them. Ears work a little bit differently. We don't necessarily have to point our ears. We can close our eyes even, and we can hear all the sounds coming from all around us. And we can do a couple things with this. Even if we close our eyes and we listen closely to the sounds, we can figure out to a certain degree of accuracy where the sound is coming from. Also, if we're familiar with the sound, we can determine what created the sound in the first place and how far away it is from us. Now, this is the exact same thing that we do with gravitational wave detectors. We build them, and then we let them sit there and listen to the universe. And when a gravitational wave passes through these detectors and measures a signal, we do the same things that I just described that we do with our ears. First, we try to figure out where the signal came from. And then using the theory of gravitational waves, we can figure out what objects created the waves in the first place. And depending on how loud the signal is, same thing with our ears, we can figure out how far away it is from us. Now the detectors up here measure different types of black holes, and these gravitational waves from these black holes live on a spectrum. This is the exact same thing as the light spectrum, except for gravitational waves. The detector on the bottom left is LIGO, which is a ground-based detector that made the initial discovery of gravitational waves in September of 2015. and it measures small black holes and other small compact objects. On the right side is pulsar timing, which is a galaxy-sized gravitational wave detector that we do not build, but we use. And this detector measures gravitational waves coming from the largest black holes in the universe, black holes that exist in the centers of galaxies. Most of my research focuses on the LISA detector in the middle. LISA is a future space-based gravitational wave detector that will measure a couple different kinds of gravitational wave events. My research focuses on events that involve at least one massive black hole existing in the center of galaxies. And for scale, these massive black holes can have masses of 1 million to even billions times the mass of our sun. Gravitational waves can help us answer many questions that we have in physics, astronomy, and cosmology, many different areas. Since we're receiving direct information about gravity in these gravitational waves, we can learn with an unparalleled view about our fundamental understanding of the theory of gravity. We can understand how correct our current theory is, and we can understand if it breaks, and if it breaks, where it breaks. And even 100 years after Einstein theorized his theory of gravity, and through the measurement of gravitational waves by LIGO, his theory from 100 years ago still holds up remarkably well. Now, after the Big Bang, there was a period of time called the Dark Ages. And as the name would suggest, there was not a lot of light propagating through the universe. Now, even though there wasn't a lot of light, there always has to be gravity. So if we can measure gravitational wave signals from this period of time, we can probe a period of time in the universe that is completely inaccessible to us with light telescopes, giving us a whole new look on a period of the universe that we don't know a lot about. Finally, the interaction of two massive black holes from the centers of galaxies is very complex. These two black holes start off in separate galaxies. The galaxies eventually come together and merge into a single galaxy. At that point, the black holes are very far away from each other and are very long orbits. And over the course of about 1 billion years, the black hole orbit shrinks to be close enough to where it can emit these gravitational waves and then collide into a final black hole. Measuring these gravitational waves will give us a great view of this process and help us learn a lot about it, especially the final stages where these black holes are so close together that we could never hope to see them with any other methods than listening for gravitational waves. Over the next several decades, the new discovery of gravitational waves will allow us to listen to the universe and answer many new and interesting questions. Thank you.